Okay, we have seen in the previous video on how to reduce the astronomical spectral data from the spectroscopy observation. Okay? And we learned that actually by dividing the target star's spectrum by that of the smooth standard star, we can actually eliminate most of the unwanted the features such as the spectral features from the Earth's atmosphere and some sensitivity variation across the spectral coverage, such as the seen in the telerecursion slide. Let's consider that actually you have the created final quality of the target spectra that are the telerecurred. Okay? How do you measure? How do you extract the physical parameters? Okay? So best way to do it is in the old days by using so-called like the 30 years old IRAF package. There's an interactive the spectrum plotting the routine called splot. I believe it is actually spectrum plot. Okay, so splot has been used widely, but as I mentioned probably earlier in the lecture note, I think during the lecture, IRAF, although that actually it has been really the used extensively for the past 3-4 the decade, it became actually the old and then outdated. So although that actually is interesting and useful to know how to use IRAF, the modern trend is actually going, I think, moving toward the Python based. So we will not use splot in our class, but we will use AstroPy's specutils package. So that the philosophy, the operating, the fundamentals are very similar. The concepts are very similar. So when you display the portion of the spectrum of your target spectrum, and then identify the spectral feature of interest. For example, in this particular one, okay, this is actually at the rest frequency. This is 6563 angstrom H alpha emission line. So from this H alpha emission line, display it after the continuum normalization, so that actually the pseudo continuum is actually the fluctuating around the one unity. So that means from that you can actually deduce that actually this spectrum was already continuum normalized. Then how to measure this intensity or strength of this the H alpha line? The simplest way is actually put a Gaussian the curve to this feature. Then Gaussian feature will actually just return some number, and that number, as shown in the bottom, okay, center and Gaussian is the EQW, means actually is the equivalent width, which will be explained in the next slide. So the spectrum they displayed in unit of angstrom. So the equivalent width should have the same the unit as the displayed or used the wavelengths unit. So equivalent width is 1.406 angstrom. What does that mean? That equivalent width of the spectral feature is basically on area under that curve. And instead of actually just changing the curved shape, and then that shape is actually just changing based on the rotational the broadening of the stars and whatnot. So the two, similar to the bandwidth calculation in the filter response function, we actually just create equal area the rectangular shape. So this the rectangular shape has a height of 1, okay, but it has the varying width, and then that width is the equivalent width, and then this rectangular the area should be the same as the area that defined by the spectral feature of interest. Okay, so pink the area is the same as the green area. In that case, that width of this rectangular, the shape is the equivalent width. So because that actually height or that 1.0 is unitless, so if you are actually multiplying by the equivalent width, which should have the same, the wavelength unit, that means actually equivalent width should have the same, the unit as the displayed, the spectrum's wavelength unit. So if the wavelength unit of the spectrum is angstrom, then equivalent width is angstrom. If the wavelength unit is nanometer, then equivalent width should also has the nanometer. Okay? So this equivalent width is the typical the term, most general term that actually that used in astronomy to denote the strength of the spectral feature. So this equivalent width can be either that the spectral feature can be either the absorption feature or maybe the emission feature as well. So there are actually just two different the school of the astronomer, and then some people that actually use the negative for the absorption feature and positive for the equivalent width of the emission feature. But some of the group actually just reverse the sign. So as long as you are consistent and then specify exactly that actually what conventions you're following, then you can actually use the equivalent with the sign as the indicator of whether it is an absorption feature or emission feature. But for our class, let's just use this the convention negative. Actually, that in our convention, because throughout the research, I use the positive because most the positive equivalent width for the absorption the features, because most lines are just absorption features from the stellar spectra. So let's use the convention of positive equivalent width for the absorption features and negative equivalent width for the emission features in our class. Okay? So now that actually you will learn in the coming Thursday's half session that how to really plot this reduced spectrum in AstroPi, and also how to calculate or the best fit the equivalent width from the spectral feature of the scientific interest. Okay? Then lastly, there are actually in the spectroscopic data reduction, there are two kinds of flats that actually one can think of. One is the flat, the calibration images taken without any the dispersion element nor a slit. So if you actually take or just flat out the images in such a case, this is actually exactly the same as the imaging mode flat. In this case, we are just focusing on the pixel to pixel sensitivity variation, right? But for the spectroscopy, in some cases, it is more useful to take the flat images taken with the exact observational setup as the target spectroscopic the observation, which means that actually that flat the calibration image is taken with a slit and then dispersion element. Okay, in this particular example, as a slit, long slit, so that slit length is actually this. That's the length of the long slit. Okay, and the dispersion axis is actually the increasing from left to the right. And this is the grading the spectroscopy observation. So that means actually that this is an unilluminated region, right? And this is actually dispersed. So there is wavelength dependent, the sensitivity variation is recorded as well. So when you are actually given a choice of using just simple imaging mode flat data versus spectroscopic mode of flat the calibration images, which one is a better choice? What do you actually want to take and use? It depends on the science that actually you want to achieve. But in a typical way, that actually flats, in principle, we are actually trying to eliminate the pixel to pixel sensitivity variation. So this top plot is the case for the simple imaging the mode flat. So no slit, no grading. Then there's the tiny undulation, and then global change is due to the sensitivity variation across the detector and then from pixel to pixel. Okay. On the bottom, when we actually just extract extract the count over certain, I think, the lengths of the data. So in which case that actually the length of the holes, the long slit, then collapse into the 1D spectrum and then display it, then you can actually see here. Okay, so this is actually just simple the flat the arc images, or it's just white light, the white light dome flat images at the spectrum. And then you can see that actually there is some the sensitivity, global spectral sensitivity variation across the whole spectral region. So which ones? Either the one or two. What? But in typical spectroscopy observations, astronomers actually just only focusing on this pixel to pixel sensitivity variation, the correction. Why? Because as we have seen in the previous case, such as like this, the telluric the correction, this can actually eliminate this overall spectroscopic sensitivity variation as well. So from the telluric correction, this global the spectral the sensitivity variation is actually automatically checked. They correct it. So in the pure, the original sense of pixel to pixel sensitivity variation correction, the typical flats and the spectroscopy observation is taken without any dispersion element or the slit. Okay? So this wraps up the spectroscopic data structure and then data reduction, the part of the lecture. And then on this coming Thursday, we will have the hands-on the demonstration on how to do this in AstroPi in reality.